Thank you for coming to our presentation. We're doing the Biomed Projects. We're doing two projects, a CPR simulator and a disinfectant chamber using ozone. So we're going to cover both of those projects, and then we'll have questions after both of the projects have continued. Done. My name is Grant Ellis.
I'm John Gertzmacher.
I'm Ben Olson.
Lauren Van Dyke.
I'm Austin Woodman.
All right, so the first project we're going to be talking about is our CPR simulator. So our project motivation was to build a physiologically accurate simulator that also teaches proper CPR. So basically we want to have the blood, in this case represented by water, flowing through the correct heart chambers and valves as compressions are being performed. We want that visible to the people around watching the CPR. And then for teaching proper CPR, a lot of current simulators in use, when you perform the compressions, there's a depth limit in place, so you compress down until you hit that, and then it won't let you press any farther. In real life, there is not a compression depth limit on when you're compressing in a human's rib cage, so we want to teach muscle memory through the use of feedback on compression depth and rate.
Here are two CPR simulators currently on the market. The one on the left is the basic model, was originally designed in 1960. This one allows for a real life experience, however, it does not give any feedback. And so you don't know how fast you're compressing or how deep. This one on the right is called a high fidelity mannequin. And this can play out many different scenarios, and it can also replicate human body function. So it can breathe, you can hear the heartbeat, the eyes will dilate, and it can pretty much replicate any human body function. It can also play out many different scenarios. So for example, if there's a cardiac arrest victim, there's a drowning accident, suffocation. So there's many different areas it can play out in scenarios. So with that comes a cost. It's almost $23,000, and where the one on the left is under $100. So many CPR training facilities do not have the means to afford one such as the right. So that's why we plan to be on the lower end of this range.
All right, so this project actually came to us already started. So there was a past group that worked on it. So in this picture over here, this is how we received the project. So as you can kind of see, it's a little aesthetically unappealing. As the base is plywood, as engineers, it's very practical because you can easily drill into it, move pieces around. However, when this is in like a physiology lab or like a health classroom, it might not look the greatest. So we're hoping to swap out that base for a plastic one just to make it a little bit more cleaner. And then we also have lack of a feedback system. So there is some wiring and circuitry over there. However, it is not working. So we would like to implement a feedback system that gives compression rate and depth feedback if you're going too slow, too fast, or like too deep or shallow. And then finally, underneath that rib cage, there is the heart chamber and valve system. So you can see the 4 heart chambers connected by one-way valves. However, the valve connections to the hearts, there's a lot of blockage in the valve itself, and then the connections between the two are not sealed properly, so it prevents proper blood flow through that. So we are hoping to fix that issue as well. So to do that, we have 4 design goals. So like I said, we want it to be physiologically accurate. So we want the water to flow through the correct order of chambers and valves when compressions are being performed. And secondly, we want lifelike compressions. So that plastic rib cage that you saw, we want it to be as lifelike as possible. So like the elasticity and stiffness of it, we want it to represent a real human rib cage. So about 100 and 125 pounds of force to compress that. And then for the live feedback, we want compression rate to be between 100 and 150 beats per minute. And then the compression depth to be between 2 and 2.4 inches in accordance with American Heart Association guidelines. And then finally, just going back to that watertight chambers and valves and just ensuring that there are no leaks in our system.
As Lauren mentioned, this project was largely constructed already, which meant that we just had a lot of testing to do. But we did have to make some decisions. And so here are 2 decision matrices. The one on the left is compression depth, and the one on the right is compression rate. So both relating to the feedback system. What the previous group had in place was 2 sets of red, green, and yellow lights. Those would indicate too deep, shallow, too fast, or too slow compressions. And they're lined up right next to each other. So we thought it could be confusing for the user and they might switch them up. And so what we ended up doing is choosing the string of lights for the compression depth. So as the user compresses down, they'll slowly illuminate the lights. The green area indicates the depth between 2 and 2.4 inches. So that will indicate that they're doing it correctly. And then there will also be faster and slower. We 3D printed some signs that will illuminate if they need to go faster or slower. Otherwise, if they're going between the 100 to 120 beats per minute, nothing will be illuminated.
So up next in this video, you will see us testing the depth sensor out. As that card ID gets brought closer to the sensor, you can see the lights illuminate here. The white light up when he's still too far away and out of range. In the green section is that 2 to 2.4 inches. And if he goes deeper or closer to the sensor than 2.4 inches, the red will light up. And then up in this next video, we will show that on the rib cage. So as he compresses the rib cage, you can see down here in this corner, the lights lighting up as he compresses deeper and also the feedback response of that sensor.
All right, so with this, we need an accurate sensor. And so the previous group had a digital analog sensor, photoelectric. And so we did some testing on it. And the main result that we found is that it's most accurate between 5.5 and 10 centimeters, which means that we want to place the sensor so that when you're compressing it, it's compressing between that range. And so basically how I did it is to set up a ruler in front of the sensor that gave the actual values, which is, or the true distance, which I have labeled here, and then I had a serial monitor running that displayed the sensor reading. And then here's our Gantt chart. So our project is a little unique. Our goal is to finish this by the end of the semester. Since we already had it kind of working already, we have a lot of the code already written. So the main thing that we still need to do is fix the leakage in the valves and get the water flowing correctly. And so that will bring us through the rest of the semester.
So here is our budget. So over here we have last year's expenses. So they spent about $550, and you can see kind of the breakdown of it. The most expensive thing was the rib cage being about $200, just because they had to outsource the plastic to get that cut and then also heat shape it to the shape of the rib cage. This year we spent about $105, and that's gone towards new silicone for heart chambers, springs, one-way valves, that new plastic base I mentioned, just to ensure those connections between the heart chambers and the one-way valves.
All right, so moving on to our disinfectant chamber here. We plan on having our ozone generated in this top part right here. And then we are planning on pushing it through a tube of manganese dioxide, which speeds and there's a lot of fluctuation in our graph. We believe that's because our wiring right now is kind of messed up from last semester. So we're trying to work through that and fix that. But otherwise, I think we can get through that pretty easily. And we will do more testing on dissipation once we get those 3D parts printed.
So here's kind of our Gantt chart for the semester and what we've all done so far and where we plan on being, just like the CPR simulator, we plan on being done by the end of this semester. So we are kind of a little unique as well in our end of the project. So we are kind of pretty much through the rest of the semester now. What we're looking to do is finish our 3D printing and run our testing and just rewire and get the wiring all done, which should be pretty simple once we get the parts all done.
So looking at our budget here, we're currently at about $140, which is about 50% more than last year's expenses. And that's because they didn't include things such as like PLA filament, which is most of our current spendings. So we are roughly about half if you include that in theirs, which is pretty good so far. I guess you have any questions for us right now, and please later follow our link here and check out our project more.
Yes,
So what will the second semester of this project look like?
we'll actually be receiving a third project that's already been started, and then working on this similar to this one and finishing that one up in the semester.
Third project is like a human lifter for, I think it's designed to be nursing homes.
Yes.
So in the first budget, I noticed you had glitter as one of the line items.
Yes.
What was that for?
So the past group, so water moving through tube isn't very visible to see that it's actually moving. So they had tested putting glitter in it so that you could actually see the fluid flow. However, what they found was the glitter kept getting clogged in the valves, which is part of why that system isn't working right now. We're thinking about dyes. We haven't quite decided on what we're going to be putting in the fluid. We're trying to get the valve and heart chambers like sealed first, that connection, before we start considering what to put in the water to make that visible.
I have a recommendation on that, just consider putting your.
Air bubbles, okay,
For collecting airs. I teach hydraulics, so
gotcha.
I found that inadvertently where I told my students to try it on such a line.
It's actually a very good idea, perfect.
Most that way to have them say, okay, just put clear acrylic line and watch.
Okay, yeah,
The plastic valves you got for the heart chambers, when you actually do the compression, it's gonna actually moving them in front of the line, that's part of the process, right?
yes. There's a clear plastic plate that sits over the top of all the chamber and valves so that the weight is, or the force is evenly distributed to compress them all.
How would you plan on testing your disinfector to detect them? Much disinfectant does.
Right now, we're actually talking with you about meeting up with the Biomed project, like the Biomed students. And they're gonna send us like Petri dishes and then we'll stick them into the disinfectant chamber and let that run for a certain amount of time. And then we'll send it back and they'll give us our bacteria levels that are on the Petri dish currently.
And you have estimates for how long this disinfecting process and scrubbing process will take. So basically from start to when you can open the chamber back up and see that.
Yeah, so currently we're sitting about like 20 seconds to reach 10 parts per million, which we've seen papers and stuff like that saying that it would roughly take like maybe 30 seconds or a minute to disinfect that object completely. And then, like I said, we would have to do some more testing on our dissipation rates. Once we get those tubes and we're able to coat them with the manganese dioxide, and then we'll just add that on to the part or to the time it takes to generate and sterilize, and we'll have our finished time and we'll work from there.
Yeah, and along with that, we're gonna run like multiple tests with it. It's not like we're gonna like just say, hey, this is what we're gonna go with. We're gonna get a couple Petri dishes, stick it in there for 5, run it, let it sit at the parts per million for 5 seconds, pull it, send them back, pull them are being sent back, or just run another test right away. Now run for 10 seconds, just keep them all labeled and then send them all back. And then there'll be a time frame where you can see where there's this much bacterial and then it gets down to, okay, this aspect it killed everything that was on here. And then we'll probably go a little bit longer than that to ensure that if it's a heavily bacterial item, that it is still disinfected.
Any other questions? If not, let's thank this team.